Good afternoon, everyone. It's quite a privilege to be able to address such a diverse audience and knowledgeable audience. Looking forward to 2050 is really an opportunity to speculate on really what is the heritage of tomorrow. I think many of the issues that we discover will transcend engineering and design, but I will interpret it through the eyes of a practicing engineer. When I started to prepare for this, the issues seemed to fall into two very distinct areas. One was where will we build? Literally, where on earth will we build? And secondly, how will technology affect what it is that we build? And these are very much our stepping stones. And I think somewhere abridging those two will be the product of the buildings as we head towards 2050. And you cannot deny that there are shifts in the economy and that somehow tall buildings are directly related to financial well-being, economic well-being. Since the early part of the last century, the tall buildings have been concentrated largely in North America, I would say, some of Europe and China and Asia. And I include China as a mature economy in this, to this extent. But I do believe that we're going to see and experience an economic shift south. China will be a mature economy by 2050. I think that Africa and South America, Central America, Indonesia, Australasia will grow immeasurably over the next 30-odd years, and that in many ways will define what it is that we do. If you take that geography literally, projects that were tall buildings that were previously defined by wind, stiffness and strength will give way to buildings that maybe at 40 stories they are more governed by seismicity and the effects of temperature. And sustainability will be a key issue in the coming years, and I believe that this changing climate will significantly affect the construct of buildings in the very near future, and we have to start acting on that now. If you really think in essence, there are very few issues that govern the design of a tall building, some of them local, some of them international. And the real skill is to pull together these well-known technologies and combine them in such a way that the technology and the geography work together to produce buildings that are consistent with their location. I'm going to take three examples very, very briefly and speak to you in engineering terms. The first one is a very tall building in Seoul that we did with Renzo Piano, Joost Mulhausen and his partner Bart Akkerhaus. This is the Landmark Tower in Seoul. 620-meter tall building is affected by the wind immensely. And part of the architectural construct was to start with a tapered form, a conical form, very much the big brother of the Shard. Our approach was not to focus on structure immediately, but to get the elevator strategy correct using sky lobbies and stacked lifts. If we got that right, then we could liberate the floor space and make this a really economic building despite the taper. Secondly, having resolved the elevators, we wanted to concentrate on the facade. That probably is the biggest influence on the environmental systems within the building. And getting that right is fundamental. Get it wrong, get the systems established, and there's no way back. Once those two things were in place, we set about the structure. It would have been very easy for us to reach out immediately for an outrigger scheme. We didn't do that. We looked at alternatives. We were very conscious that the core could be affected by outriggers and indeed sized by the outriggers. So we looked at alternatives. You can see from these diagrams on the left that the stresses put into the core by this system are quite high, well known to many people in this room. There was an alternative, we felt, and we investigated because of the virtues of a conical form, wrapping a double helix around it. What that meant was that every piece of structure, every floor, all parts of the core are gently engaged. They are gently engaged and they give us much more inherent damping. And as you can see from the diagram on the right, the forces that were very acute are now smoothed out across the whole core, and there's an interplay between the outer skin and the core. And the forces that puts into the floors were all manageable. In composition, what you see is this. That by itself, by definition, is an example of a strength-governed structure. If we look at what it is that we do in confined sites, this job was in Tokyo with Renzo Piano one more time. Very slender, 10-meter site. We were intrigued by the performance of pagodas because they had a mystical status in that part of the world, in that they withstood earthquakes well. We exploited that technology and introduced a stepping column. Pagoda works because it changes stiffness under lateral load. It's a period shift. It sucks less energy out of the ground. Using that, we developed a damping system, and we cut the column at the back of the building, which gave period shift and reduced stiffness, therefore less force. The net effect of that was to reduce the overturning moment at the base by approximately 40% and remain elastic. So in a really critical condition of an intense earthquake, the building would remain serviceable. We were able to quantify that on behalf of the client, Jean-Louis Dumas, and that, of course, affected directly his ability to gain insurance and to benefit his business in that sense, and make use of almost what was previously a useless but a very, very small site, 10 meters by 50 meters, and it liberated one side of the building to give space to the site. It was with that in mind, we designed it 15 years ago, and it's been in service for the last 13 years, and it withstood the earthquake in Tokyo very, very well. We lost a ceiling tile in the earthquake of 2011, and that was the extent of the damage. We moved then, so with this confidence, we moved into a project in Mexico, which had a completely different set of problems. The ground in Tokyo is hard, the earthquake intensity is high. In Mexico, the seismic effects are equally important, but the effects are different. And in Mexico, we had a very, very benign climate and a very particular response to earthquakes and very, very poor infrastructure, which I'll come on to. Explaining what actually happens in such a complex seismic zone is difficult, so we built a model to try and explain that. As you can see, my hand on the table is putting a very small force into that piece of jelly. That piece of jelly then responds, sending an amplified signal up to the building above. And as you can see, when the mass above resonates with the jelly, you get excessive movement and excessive forces. We wanted to avoid that, but trying to express that to a lay body is quite difficult. However, what you see there is actually the principles of the design criteria that we used to develop our tower in Mexico. You will see from this diagram that there's a huge block at the bottom of the tower. That is to house 2,800 cars. Compare that with the Shard, which had only 48 car parking spaces. There is no infrastructure in Mexico City. You inherit a huge carbon footprint as a result of building in these geographies. We decided also to make the building as light and as ductile as possible. For that, we used an external megaframe with no core. The climate affected the systems within the building. It gave us the opportunity to downspec the facade and cut direct sunlight by using a veil on the outside of the building. The four sides are different. They are different because they react differently to each elevation, and the way that the sun hits that albeit that there's a very high sunpath in Mexico. We could look at opening windows at certain points, and we could free the facade, hang the facade as a curtain over 3 stories to absorb seismic deformations. And here you can see the mock-up of the facade. You can see the external omega frame, which actually characterizes the building. All in all, we built that for 17,000 tons, which over 55 floors gave us a very, very economic structure at less than 150 kilograms square meter. The key to that was to develop an energy absorbing system, which we did in the EBF, and you can see the effect with time, the time history of stresses induced as a result of an earthquake. It is controlled ductility, it is controlled failure. That means that it takes stress out of the system as a whole, it takes force out of the system as a whole, and makes the performance of the structure that much more economic. Some snapshots of this actually being built and going up. We're about level 27 at the moment. With that in mind, we make a very clear case for designing for geography, that we cannot simply transport designs, templates from one country to another and hope that they work. There has to be a conscious decision on form. But just by way of a little fun, what we did was to test that. And we took 4 of our buildings, and in a digital sense, we moved them around the world. We were very keen to see how they would perform in new geographies. So we took the Gherkin and we took it to Mexico City. And what is an absolutely fantastic building in London, less than 130 kgs a square meter, that gets the wind for free by virtue of its geometry and its construction. Take it to Mexico, and you can see that you increase the base shear on the building by a factor of 17. Those of you in the room that practice seismic engineering will understand that there are ways of reducing seismic forces. I doubt very much by that much. Equally, we then shifted Leadenhall to a similar location, and the base shear increased to a factor of 10. But the real issue there was that the top of the building was overstressed. It picked up a hide-mow response. So the way that building vibrated induced forces at high level that would, if left untreated, could shear the top of the building. So again, much of this is soluble, but it's demonstrating that there are appropriate forms for geographies. There are designs that suit particular locations. Converse, shifting our BBVA model to London, it performed reasonably well. It was about 1/8 of the base shear elastic that we developed in Mexico. And what this is meant to show, and hopefully does show, is that when we pass this amplified signal that comes through the jelly of Mexico City into the structure, we are not getting what we would term a mode 1 response. That is to say, the building is snaking. And the way it snakes and the forces that draws in are dissipated in a controlled manner. This demonstrates the way in which the structure would fail or would yield in a catastrophic event, and were that to ever materialize, most of Mexico City would be wiped out anyway. But this building is life safe and could be, under certain circumstances, refurbished. So, just to try and wrap up very, very quickly, when we do move to these new countries and we do find the new forms, our experience in China, our experience in Hong Kong when I was there in '82, and certain places like Dubai, there has been a natural cycle to which costs become stabilized, that techniques are stabilized, that knowledge of the industry grows, and I would suggest that that's about a construction cycle, 2 construction cycles, maybe 5 to 7 years. So that gives the emerging economies time to think and prepare. Time to think and prepare for what? Well, I think that the lessons learned in a geographical sense, particularly in Asia, where in the last 10 years they've built more tall buildings than the rest of the world in the last 50. That there is a responsibility to the industry in that world to share knowledge. There is a responsibility to lead because there are important lessons learned in the construction of high-rise buildings. In those parts of the world in which the tall building is well established, I think the responsibilities lie there in refurbishing and caring for the buildings that already exist. There is a responsibility to improve the energy performance of those buildings, maybe in the cladding, and most of all, to take care of the infrastructure that serves those buildings, because tall buildings are ever so reliant on good infrastructure. I think we've heard that time and time again at this conference. And then there are those parts of the world that have tolerated the high buildings, tall buildings, and I include London in that. I think we've woken up in the last 10 years. However, London is a fantastic place to build tall buildings. The climate is benign. We don't have earthquakes. It's not too windy. The ground isn't bad. It's possible to make some fantastic projects in and under these conditions. But to do that, we need to keep our transport hubs up to date. We need to think about some of the things Peter aired to yesterday morning, of having good strategic planning and really finding political support for the construction industry and what it wants to achieve. But the real incentives, I feel, lie in Central, South America, some of Africa, and India. And India is in some ways an established economy, but is growing at an incredible rate. And when moving to these areas, I really think that there's time now to get it right. Not a lot of time to get it right. What do I mean by getting it right? I mean that the codes and standards need to be brought up to date to reflect best international practice. The Council of Tall Buildings did wonderful work in introducing performance-based design. I think that needs now to be embedded into the codes and regulations of these emerging economies very, very quickly, so that when this wave comes through, it's ready for it. It's important to get the planning aims correct, that the city planning is well thought through, and how that would relate to what we have in London, I do not know, but maybe that's a question for others in the audience. But really, to find some governmental and economic policies that are consistent and stable over a period to give the entrepreneurs, the investors, the opportunity to invest with some confidence. I think those 3 or 4 things are absolutely essential throughout South America, Central America, and really what are the emerging economies. So if I were to answer or put responses to my stepping stones, what would they be? I would say that the where component, the geographical component, is very definitely China. It is South America, it is India. China is an established economy in these terms and will power on. I see the what, the technological element to what it is that we are trying to achieve, largely focusing on energy consumption and infrastructure, which is a strange thing to say for a structural engineer interested in tall buildings. But these really are the key issues in my view. Time and time again we come across it. And finally, I think it's to design with appropriate technology. That is to say, not transporting template designs, forcing them on the local market and literally hoping that they work. I think we've made a fatal mistake if we carry on in that way. Really, just to close down, as I've been given my marching orders, I started work in Arabs in 1982. I started work on Chaiwan Depot at the same time Ken was working on the bank. I wasn't too happy with that. I felt that working on the mass housing project was a kind of second-class role. But what you see in Hong Kong now is that the techniques we perfected in the late 70s, early 80s have been replicated ad nauseum. And somehow, if the cities continue to grow throughout, densification is a real issue. And we've got to find a way of making Chaiwan Depot a pleasant place to live, because the constant gobbling up of land, particularly in Britain, is simply not acceptable. I'll leave you with that thought. Thank you.